Hello students, welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. Hope the earlier videos have been useful for you all. In this video, we would be studying about electric flux, what are the properties of the electric flux, about Gauss law, applications of the Gauss law in finding electric field for infinite line charge, for infinite sheet of charge and the spherical shell. Let us begin with electric flux. How do we define electric flux? The electric flux is defined as the number of field lines passed through a given area held normal to the direction of electric field. So the number of field lines passing through a given area held normal to the direction of electric field would help us in defining electric flux. The number of field lines passing through the given area dA would be given by d phi equals E dot dA. Now flux from the entire closed surface, then it can be written as phi closed surface integration d phi. Then it would be closed surface integration E dot dA. So this sign represents the closed surface integration. Flux is also the directed motion in any given direction of electric field lines. So flux is nothing but the number of field lines that would be passing through a given area held perpendicular to the direction of electric field. Now the question is, what are the different properties of the electric flux? So a scalar, I can say electric flux is a scalar quantity. Why? Because it is being defined by the scalar product. Now when it comes to the unit, then its unit is Newton per coulomb into meter square, or it can be defined as volt into meter. Now what are the dimensions? Then dimensions for the force m1 L1 t power minus 2, for the charge a1 t power 1, and area L square. So resulting dimensions would be m1 L3 t power minus 3 ampere power minus 1. Now we can say flux is a property of vector fields. Why? Because vector has a directional nature. So we have already said that directed motion of electric field lines would be called as flux. So flux is always related to some vector field. We can have flux of electric field, we can have flux of magnetic field, we can also think about the flux of gravitational fields. So we can basically say flux is a property of vector fields. Now there are two things that we want to say. What does the flux from a closed surface depend upon, and what does the flux from a closed surface does not depend upon? So point number 3, it says flux from a closed surface depends on. It depends on magnitude and polarity of the enclosed charge. It also depends upon nature of the medium surrounding the charge, and it depends upon orientation of area with respect to direction of electric field. So I can imagine an area like this. Then in this case the direction of the normal is like this. I can also imagine an area like this. Then the direction of the normal is like this. Suppose this represents the direction of electric field. Then what happens? Through this situation the flux of the electric field would be maximum, and in this case the flux through this area would be minimum. That is why we say it depends upon orientation of area with respect to direction of electric field, because in the flux it is E dot dA, which means E dA cos theta. And what does theta represent? It represents the angle between the normal to the area and direction of electric field. If theta becomes 0, cos 0 would be 1, and in that case the flux comes out to be maximum. If theta becomes equal to pi by 2, then what happens? Cos pi by 2 would be 0, and in that case the flux through that situation would be minimum. Now what does the flux from a closed surface does not depend upon? It does not depend upon position and distribution of charges inside the closed surface. So in a closed surface, whatever be the position of the charge, how are they distributed does not make any change on the number of field lines passing or coming out of that surface. Suppose I have a single charge of 5 coulomb, or I may have a charge of 1, 2 and 2 coulombs. In both the cases, the flux from the closed surface would come out to be equal. That is why we say it is independent of position and distribution of the charges. Shape and size of the closed surface. Even if I choose a cuboid of length 1 meter, or I may choose a cuboid of length 2 meter. If I keep a charge of 2 coulomb inside the surface, then the number of field lines would definitely be same. Then presence of an external charge. Flux from a closed surface depends only on the internal charge. It has nothing to do with the charges that are present outside the surface. Now, what does the sign convention say? The sign convention says the inward flux is taken negative while outward flux is taken positive. Suppose this represents the direction of electric field. Then this is the direction of the electric field. This would be the direction of the normal to this area. Then theta is 0. So E dot dA would be E into dA, which is positive. So the outward flux is taken positive. In this case, what happens? This would be the direction of electric field. This would be the direction of normal, and the angle between the two is 180. In that case, cos 180 is -1, and that is why we say inward flux is negative. So for the surface A, theta is equal to 0, cos 0 would be 1, positive flux. For the surface B, theta is 180, cos 180 is -1, and that is why we say flux is negative. So inward flux to be taken negative and outward flux to be taken positive. That is the sign convention that will obey for the flux from now on. Now let us imagine a situation. When a dipole is enclosed inside the cube, what would be the net outward flux? Whenever we say dipole, then dipole is a system of equal and opposite positive and negative charge. Now both the charges are equal. For the positive charge, it would generate net outward flux. For the negative charge, it would generate net inward flux. Since the charges are equal in magnitude, so field lines inward and outward would be same. So what would be the net outward flux in this case? The net outward flux would be 0, because outward flux due to positive charge will be equal to the inward flux due to negative charge. Another situation, what happens now? We have when a closed cuboid is placed in a uniform electric field, what would be the net outward flux from the cuboid? Now, if you place a cuboid in the field which is uniform, that means uniform field would always have equally spaced electric field lines in the same direction. So number of field lines entering the cuboid would be same as number of field lines leaving the cuboid, and in that case, once again, the net outward flux would be 0. Then we have, if the radius of the sphere is doubled, then what will be the effect on net outward flux? There would be no effect of net outward flux. Why? Because we have already said that the net outward flux is independent of shape and size of the surface. Because number of field lines is always decided by the magnitude of the charge, not by the shape and size of the surface. Now we would like to utilize here something called three-dimensional angle, normally called as solid angle. Let us first think about how did we think about the two-dimensional angle. The two-dimensional angle is defined as the ratio of arc and radius. Angle theta is equal to arc P1 upon P1 P2 upon arc. So the maximum value of angle theta can be decided by the maximum value of the arc P1 P2, and the maximum value of the arc P1 P2 would be equal to circumference, that is 2 pi r. So 2 pi r upon r, so r cancels out here. So maximum value of theta is 2 pi radian. So what is the angle here at O about this point, and that is 2 pi radian. Similarly, let us think about the three-dimensional angle. When it comes to the three-dimensional angle, let us imagine a cone here. When I say cone here, it has an area here. The direction of the area is given by the direction of the normal. So this would be the direction of area vector, that is along n cap. The angle that would be subtended by this area at the vertex of this cone would be called as the solid angle. Now this area may be inclined like this. So this would be the direction of the normal. Now I can have two components of the area vector, dA cos theta in this direction and dA sin theta in this direction. How do I define solid angle? As the ratio of normal area upon r square. And what is the normal component of the area? dA cos theta. So it is dA cos theta upon r square. What can be the maximum value of the solid angle? It would be defined by the maximum value of dA and maximum value of cos theta. Maximum value of cos theta is 1 and maximum dA, that is equal to surface area of the sphere, and that would be 4 pi r square. That is why these r squares here would cancel each other. And finally we have the maximum value as 4 pi steradian. Now certain things need to be remembered by us. What are the important conclusions that we have drawn? The three-dimensional solid angle is defined as d omega equals normal area upon r square is equal to dA cos theta upon r square. The angle subtended by the entire spherical surface at an internal point is 4 pi steradian, already proved by us. The angle subtended by the complete spherical surface at an external point would be 0. So when it comes at an internal point like this, then it comes as 4 pi steradian. But if the point is situated outside the sphere, then the angle subtended by the complete spherical surface at an external point would be 0. These facts would be used to prove Gauss law. Now what is Gauss law? Gauss law is a method by which we can calculate electric field produced by symmetric charge distributions. What type of symmetric charge distribution? Symmetric continuous charge distribution. What does that say? The net flux of net electric field from a closed surface is equal to the ratio of total charge inside the closed surface to epsilon naught. So flux of net electric field. What does that mean? It says electric field can be produced by the charges inside the closed surface as well as outside the closed surface. But the flux would only depend upon the ratio of total charge inside the closed surface to epsilon 0. So flux will only depend upon the magnitude and the polarity of the charge inside the closed surface, while the electric field may be contributed by the internal as well as the external charges. Now we can always prove Gauss law for an internal charge. So let us imagine a closed surface here. This is the spherical closed surface S. Here we choose a small area here. The direction of the normal is like this. We have a charge Q here, which would generate an electric field, and the electric field would be radially outwards. So we have this as the direction of electric field. Now let us just see here. We consider a charge Q which is enclosed inside the surface S. The electric field produced by this charge at the point P would be given by 1 upon 4 pi epsilon 0, that is K Q upon R square. Then what would be the flux through this small area dA? So this flux through the area dA would be given by d phi, would be E dot dA. What would be the flux through the entire closed surface S? Then phi would be equal to integration E dot dA, and this integration is over the entire surface S. Now what does theta represent? As usual, the angle between the direction of electric field and the direction of area vector, which is along the direction of normal. In our case, in this figure, theta is equal to 0, and that is why cos theta would be equal to 1. So this can be written as Q upon 4 pi epsilon 0 integration dA cos theta upon R square. And what does that represent? It represents the solid angle d omega. The angle which is subtended by the area element dA at the point O. This is what is shown in the figure here. This is area here dA. It is subtending some angle at the center, and therefore this angle would be called as the solid angle. Now integration d omega would be equal to 4 pi. Why? We have already proved angle subtended by the complete surface at an internal point O would be equal to 4 pi. So phi would be equal to q upon 4 pi epsilon 0 into 4 pi. 4 pi cancels out here. This cancels out. So phi would be equal to q upon epsilon 0 equals 4 pi kq. K is as usual the electrostatic constant. So for an internal point, phi is equal to ratio of charge inside the closed surface to epsilon 0, which is Gauss law. Now flux due to external charge q. So we have an external charge placed here as q at point O. Again we choose a surface here. What will happen? It would subtend a solid angle at this point O, and that would be called as d omega. So what would be the flux from the closed surface? Phi would be equal to closed surface integration E dot dA would be equal to E dA cos theta. The electric field due to external charge at point P is equal to 1 upon 4 pi epsilon 0 q upon r square. So see, electric field is being contributed in the first case by internal charge, and in this case it is being contributed by external charge. So phi would be now equal to q upon 4 pi epsilon 0 dA cos theta, and that is nothing but the solid angle. So d omega is the angle subtended by the area element dA at the point O, that is external point O. And integration d omega would be 0. Why? Because the angle subtended by the complete surface at an external point O would be 0. So flux due to external charge is 0. Now let us find out what important things one can say about Gauss law. So we here say Gauss law is used to calculate electric field of continuous charge distribution. For all continuous charge distribution like line charge, surface charge, volume charge, we are supposed to calculate their electric fields with the help of Gauss law. Gauss law is applicable for closed surfaces. If suppose there is no closed surface, then we have to imagine a closed surface so as to apply the Gauss law. Gauss law is applicable for the closed surfaces. So if there is no closed surface, then we need to have a closed surface just before applying the Gauss law. The electric field that appears in the Gauss law, we have already shown it can be due to internal as well as external charges. Because external charge capital Q, that also had the electric field, and internal charge that also produced electric field. So electric field can be due to internal as well as external charges. Now flux from the closed surface is only due to internal charges, already proved by us. Now Gauss law is based on the inverse square dependence on distance contained in the Coulomb's law. Any violation of Gauss law will indicate departure from inverse law. That means Gauss law is applicable for the fields which obey inverse square law. Hope Gauss law is clear to all of you. So students, if you are able to follow what is being done in this video or the physics lectures that are being put up in the channel, you are all requested to like and subscribe the channel. You can also press bell icon button so that all further videos notification will reach you in time. Once again, request for subscribing the channel. Now we would like to understand what are the basic applications of the Gauss law. The first application says electric field due to infinitely long straight uniformly charged wire. So we have a wire here. On this wire, let us choose two small elements here at the points P1 and P2. So we have a infinitely long, straight, thin wire, which is described by uniform line charge density. We consider two small elements of length dl at the points P1 and P2. So one dl placed here, another dl would be placed here. The charges dq at the point P1, because these two dls would have some charge, and let that be called as dq. They will be producing some electric field at the point of observation P here. So at this point, these charges which are placed at the point P1 and P2 would be producing some electric field here. So let us calculate what are the electric fields produced. So I can say the charges dq at the point P1 and P2 produce electric field at point P, which are equal in magnitude. So from the figure you can say the distance OP is equal to R. Similarly, the distance P1 and P2 are equal. Similarly, distance OP2 and OP1 are also equal. So let us say OP would be equal to R, OP1 is equal to OP2 is equal to Y. The electric field due to charges dq at P1 and P2 on the point P would be given by K dq upon R square plus Y square. Since both the fields are equal, let them called as dE. Now what happens in this figure? These two d's, we have one component of the electric field from the charge at P2, another component of the field from the charge at P1. Resolve them into two components. The horizontal components would be dA cos theta here, and the vertical components would be dE sin theta here. The two sine components are equal in magnitude, opposite in direction, and they pass through the same point and therefore are supposed to cancel each other. So every charge dq would be contributing one component dE cos theta along OP. Since every charge is contributing a component dE cos theta and which is along the same direction OP, so the direction of the net electric field would always be perpendicular to the line charge, that is along OP. So we are able to determine what would be the direction of the electric field that would be produced by the line charge. Now we are supposed to calculate what would be the magnitude. For that, we imagine here a Gaussian cylinder. That means at the point P I need to calculate the electric field, but what do I observe? There is no closed surface. Before the application of the Gauss law, I am supposed to imagine a closed surface. So I imagine a cylindrical surface. Then cylindrical surface has a height h and the radius is r. So we imagine a cylindrical Gaussian surface of height h and radius r. Now what does the Gauss law say? Integration E dot dA is equal to charge inside the closed surface to epsilon 0. This closed surface is made up of three parts: the first circular surface, the second circular surface, and the cylindrical surface. So the field lines can be made to come out either of the two circular surfaces or the cylindrical surface. That is why we write E dA cos theta over the first circular surface, second circular surface, and cylindrical surface. For the closed surfaces, this is the direction of the electric field, and this would be the direction of the normal. So theta is 90. So for the first circular surface, theta is 90, cos 90 is 0. For the second circular surface, theta is 90, cos 90 is equal to 0. But for the cylindrical surface, what do we find? We find the direction of electric field and the direction of the normal are same, so theta must be equal to 0. So cos 0 has to be 1. So the first integration here vanishes, second vanishes, and on the third one we can write E dA over cylindrical surface. Then what would be the value of a charge inside the closed surface? Because lambda is the charge density and h is the height, so total charge inside the closed surface would be lambda times h. So E integration dA over the entire cylindrical surface must be equal to lambda h upon epsilon 0. Now what is the surface area of the cylinder? 2 pi RH. So integration dA would be equal to surface area of the cylinder, 2 pi RH. So this h cancels on both the sides. So electric field would be equal to 1 upon 2 pi epsilon 0 lambda upon r n cap, or it could be written as 2k lambda upon r n cap. the direction of the electric field is along the direction of the normal. So what does the electric field due to infinite long conductor depend upon? It depends upon nature of medium surrounding the line charge through epsilon. It also depends upon line charge density. More is the line charge density, more would be the strength of electric field. You can always plot a graph between E and lambda. It would come out to be a straight line passing through the origin. Distance of point of observation. So if we want to plot a graph between electric field and the distance of point of observation, as r increases, the electric field continues to decrease. It is as good as a rectangular hyperbola. So here are the two graphs: electric field proportional to lambda and electric field proportional to 1 upon r. This shape is basically called as the rectangular hyperbola, and this is a straight line passing through the origin. So students, I think we are clear with how to calculate electric field due to infinite line charge. Now, as the second application, we would like to calculate electric field due to uniformly charged infinite plane sheet. So here once again we pick up a sheet of charge. At the point P, we need to calculate the electric field. So we imagine two area elements dA which are placed at the point A and B respectively. Both A and B are equidistant from this origin O. The distance OA and OB is equal to y and OP is equal to r, as in the earlier case. AP is equal to BP and would be equal to under root of r square plus y square. To describe the charge, uniformly charged sheet, we use the concept of uniform charge density. dA is small area element and dq charge on this area element. Now there would be some electric field produced by the charge at dq at A, and that would be equal to dEA, which would be equal to k dq upon AP ka square, which can be written as k dq upon r square plus y square. Similarly, I can calculate what would be the electric field due to charge at B, and it would be same in magnitude as k dq upon r square plus y square. So what do we find? The two electric fields are once again equal. Then you can always resolve them into two components, and one of the component would be the sine component, other would be the cosine component, and in our figure what we find, the sine components are equal in magnitude, opposite in direction, act along the same line, so need to cancel each other. Once again I can say every charge at dq is contributing only one component dE cos theta to the electric field, which is perpendicular to the sheet of charge. So when it comes to asserting the direction of the electric field, I can just conclude. I can say the direction of electric field is always perpendicular to the sheet of charge. So in the first case, when it was line charge, I said the direction of electric field is perpendicular to the line charge. And similarly, when it comes to the sheet, we have the same rule, and it says direction of electric field would always be perpendicular to the sheet of charge. Now, by using the Gauss law, we need to calculate what would be the magnitude of the electric field. To calculate the magnitude of electric field, what I do is I imagine a closed Gaussian surface. So we imagine this surface as the closed Gaussian surface. So we have written here, we choose an infinite plane sheet with a uniform surface charge density sigma. X will be the normal to the given plane. So by symmetry, what will happen? I can say that no electric field would be existing in the upper face and the bottom face. That is the plane that would be lying in the YZ direction. Both planes do not have any electric field lines passing through them. Why? Because the direction of electric field is horizontal, direction of the normals would be vertical, and in that case theta would come out to be 90, and that is why we say that no electric field would be passing through the YZ plane. Then I can imagine I may have something called XZ plane also. when it comes to the xz plane, the direction of the electric field is horizontal, but the normal is perpendicular. So once again, for both the planes, theta comes out to be 90. The only two planes that would be contributing to the field lines passing through them is plane number 1 and 2, which would be lying in, I can say, YZ direction. So let us say by symmetry no field would be existing in Y and Z direction. So we take a Gaussian surface as a rectangular parallelepiped of cross-sectional area A. Here only two surfaces 1 and 2 will contribute to the electric flux. For all other surfaces, the field lines are parallel to the surface, so no electric field would be passing through them. So they do not contribute to electric flux. As per the Gauss law, phi must be integration E dot dA must be equal to Q inside upon epsilon 0. So integration E dot dA cos theta over the first surface and second surface would be Q inside upon epsilon 0. In both these cases, theta comes out to be 0, cos 0 would be 1. And what is the value of the charge inside the closed surface? It would be sigma times A. A is the area of cross section. So I have E integration dA over the first surface, E integration dA over the second surface would be sigma A upon epsilon 0. So integration dA would be equal to the cross sectional area A. So in LHS, twice EA would be sigma A upon epsilon 0, or E is equal to sigma upon 2 epsilon 0. In the vector notation, electric field E would be equal to sigma upon 2 epsilon 0 n cap. Now, for the first time we have obtained an relation for electric field sigma upon 2 epsilon 0, which does not contain R. It only depends on charge density and the medium surrounding the sheet of charge. So the sheet of charge produces a uniform electric field because sigma is constant and the medium is same. The electric field of uniformly charged infinite plane sheet is independent of R for the first time. The electric field depends on the uniform charge density sigma and the nature of medium surrounding the sheet of charge. So we have found out a method by which we are able to calculate certain situation where electric field is uniform and independent of R. That is distance of point of observation, and the infinite plane sheet provides us a field which is either independent of R and also it's uniform. Hope we are very clear about infinite sheet of charge, the electric field, how to determine, and what are the properties of the electric field that has been produced by the sheet of charge. Now, dear students, once again we are now using in the third application Gauss law to calculate electric field due to a uniformly charged thin spherical shell. Now we have a thin spherical shell here, and when I say thin spherical shell, it is as good as a hollow sphere. So we have a thin spherical shell of radius r, uniform surface charge density sigma. So this is the spherical shell. It carries a total charge q and it has a charge density sigma. R is the radius of the sphere. Now I need to calculate what is electric field at this point P, which is outside the sphere. It is at a distance r, and remember r is greater than r. So at this point we do not find any closed surface, so we imagine a closed Gaussian sphere as the closed surface. Choose a small area dA. The direction of the normal would be like this, and the direction of the electric field due to this charge q would be also outward. Since the charge q is positive, the direction of the field would be once again radially outward. So we have said we consider a point P0 outside the shell with radius vector r. We have chosen a Gaussian surface as a sphere of radius small r with center O. All the points on the surface are at the same distance with respect to point O, and that is what is known as the spherical symmetry. As per the Gauss law, integration E dot dA must be q inside upon epsilon 0, theta is 0, cos 0 is 1, q inside is the total charge. So E integration dA must be q upon epsilon naught. What is integration dA? It is the total surface area of the Gaussian cylinder sphere, and that would be 4 pi r square. So E into 4 pi r square is q upon epsilon 0. To calculate the electric field comes out as 1 upon 4 pi epsilon 0 q upon r square is equal to kq upon r square. In vector notation, it is kq upon r square r cap. By looking at this field, it gives me the feeling that electric field is same as the electric field that was obtained by the point charge. So that is what we have written here. The electric field at an external point due to spherical charge distribution is same as the electric field produced by a point charge q placed at its center. That means, what does it say? If I place a point charge at the center of the sphere, it would produce same electric field at the point P0 as produced by the spherical distribution of charge. That means, for an external point, the spherical charge just behaves like a point charge. That's an important conclusion that we have come across. For external point, the charge distribution is meaningless. It is behaving as good as a point charge. Now what happens? I can always choose a point on the surface of the sphere. At the surface, the variable distance r would be equal to the radius of the sphere, and in that case kq upon r square would be the strength of the field. And remember, electric field, this value is the maximum, and that is at the surface of the sphere the electric field would always be maximum. Now what happens at an internal point? Let us find out. Now this represents the charge distribution. This is the radius of the sphere. The total charge on here is q. We choose a point inside here. There is no Gaussian surface, so we imagine a sphere of Gauss as the Gaussian surface of radius is small r. So let P be inside the shell. The Gaussian surface is a sphere through the point P with the center O. Now what happens as per Gauss law? Definition says integration E dot dA must be equal to q inside upon epsilon 0. E dA cos theta would be and q inside upon epsilon 0. But what is the value of the charge inside the closed surface? All the charge is on the outer surface of the sphere. So no charge is enclosed by the Gaussian surface. So Qin would be equal to 0. So I can obtain E into 4 pi r square would be 0. That is, electric field is 0 when r is less than r. The field due to uniformly charged thin spherical shell is 0 at all places inside the shell. That's an important part of this. I can imagine like this. Suppose I have a sphere here. So I can always plot a graph. Now remember, at this point, that is the surface point, that is r is equal to r. This is also a point on the surface, r is equal to r. Inside, the electric field is 0. At this point, electric field is a maximum, and that is kq upon r square. Here also the electric field is a maximum and is equal to kq upon r square. Now outside it decreases as 1 upon r square. So this is spherical charge distribution and three fields existing here. At the internal point, at the point on the surface, at the point inside the surface. Since charge is residing on the surface, we do not have any electric field inside the shell. At the surface, the electric field comes out to be maximum, and outside it decreases as 1 upon r square. Hope that all applications of the Gauss law are very clearly understood by you all. मैं वापस से आप सभी से एक बार रिक्वेस्ट करता हूं कि यदि आपने इस चैनल को अभी तक सब्सक्राइब नहीं किया है तो एक बार इसे लाइक और सब्सक्राइब करें. बेल आइकन के बटन को अगर आप दबा देंगे तो उसके बाद जो भी नए वीडियो आएंगे उसके नोटिफिकेशन आपको टाइम पर मिल जाएंगे. थैंक यू वंस अगेन. थैंक यू ऑल.